So let's go ahead and date it. Today is August 25th. Initially here, I don't know how much you're going to be able to write down. All right, we are actually going to start section 1-1. All right, and this is a preview of calculus. Okay, so you can download my online notes, all right, and have a copy of all this because I've got it nice, neat, typed up. The first 3 pages of the notes are all nice, neat, and typed. Okay, so I'm going to go ahead and zoom in here. All right, let's just talk about this a little bit. So a lot of this today is going to be conceptual. All right, I need you to grasp the idea of what's going on here before we get into too much. That's why I said it's a preview of what calculus is. All right, so we're going to find out as we go through this year that calculus is really the study of change. All right, everything in the world around us, things change. And as something changes, it affects something else. All right, and so that's what calculus does. It explains the world around us and it calculates and can figure out, well, what is that change and how's that change impacting something else? Okay, so that's like the overall big thing here. All right, I also wrote a sentence on here, what calculus is the mathematics of velocities, accelerations. All right, in physics last year, you probably did a lot with acceleration and velocity, all right, different moving projectiles and things like that. And you did it from probably an algebra base, okay, the way you calculated your acceleration or your velocities in physics last year because you didn't have the calculus yet. So they couldn't do physics. I am right, you did take physics, right? Yeah, okay, good. All right, you could not have done a physics based on calculus because you hadn't had it yet. Okay, so there's a couple different ways physics can be taught. There's a lot of involvement with tangent lines and slopes. We're going to look at that today. We're going to look at areas and how that's going to start to play. And then we're also going to do volumes, all right? And all of these things, your tangent lines and slopes and areas and velocity and acceleration, what it does is it allows people, like say scientists and engineers and people like that to model real world situations. Okay, it allows them to model real world situations. We did some mathematical modeling last year in pre-calc, right? I had you do some pictures and we did mathematical modeling because it was the easiest, because you can't really, at your level of mathematics, you can't really do true mathematical modeling. But what we did, we took pictures of things that we saw that looked like maybe say a cubic equation. And then we allowed the calculator, we dropped some points on there. When we were dropping points on those curves, we were collecting data. We were collecting data points. All right, and then the calculator took those data points and built the mathematical model that represented, say, the x to the third equation. Okay, so in real world applications, what do scientists do? They collect data points and then they can build a mathematical model that represents that, and then it can tell them something. Okay, so now might as well be a good time as any to do this. All right, let's say we all know Eli Lilly, right? Company, they produce drugs, right? So your scientist develops a new drug. And then what do they do with that new drug? They take it and they usually run trials. I mean, actually the coronavirus right now, what are they doing? They're trying to make it an immunization and then they're going to run human trials on that, right? So any drug, it works that way. Okay, well then when they run those human trials, data is collected and it comes back to Eli Lilly. Okay. Now, generally, it's probably not going to go directly back to the scientist first. All right, it may go to the mathematician that works there. And then that mathematician is going to take that data and build a mathematical model. All right, on a general drug, any type of drug, what do we want it to do? We want it to have a high success rate as possible. All right, so that's what we're trying to do. We're trying to maximize the benefit of that drug. All right, it's a maximum problem. All right, an optimization. We want to optimize what that drug does for the person. Okay, so that's once they get that mathematical model, all right, then they can perform some things and then they can make decisions about, okay, they're going to change the drug this way, they're going to change it that way. Okay, and then obviously it goes back and forth. All right, as you saw with this COVID thing, they had mathematical models at the beginning that predicted how many cases, how many people were going to die. And then they were kind of off, right, at the beginning. Why? because the amount of data that they collected at the beginning, they didn't have a lot of data. Okay, so their model was not as accurate as could have been. But as they get more data, then they build new mathematical models and it makes their predictions better. So, well, yeah, yes, in general, when they collect the data, there's always human error in anything we do, right? So when they collect the data, if it's not reported appropriately, then it skews it, which then would throw off the mathematical model. Okay, so when you run an experiment, when you collect data, your science teachers have tried to get you to, hey, you need to be precise when you take those measurements, okay? Because you don't want that human error involved in it. Okay, so that's actually the overall broad view of what calculus is, okay? Now, we're going to take a look at some different scenarios in math here, all right? How we handled them in pre-calc versus how we're going to handle them in calculus. All right, so in this example right here, let's say I've got some random curve f of x, and I've picked a random number on the x-axis. All right, what could we do in pre-calc? Well, we could what? Take that x value, plug it into the function, and it would tell me exactly what y is. All right, and that's obviously no calculus whatsoever. You did that in pre-calc. All right, but what we're going to be able to do, and we saw a little bit this last year when we took a little bit of look at the limits. All right, but we're going to be able to find the limit of the function as it approaches c from both directions. All right, that's something we could not do with just pre-calc knowledge. When I started talking about limits last year, all right, that was introducing you to calculus, okay? What have you always been able to do since about algebra 1? You've always been able to find the slope of a straight line, right? Because it's very constant, it's static. It has a rise over a run. It has a change in the x and a change in the y value. And it's a linear line, so it does the same thing, right? Rise, run, and it's very constant. That slope does not change at any point along that line. Okay, however, now what we're going to do, we're going to be taking a look at some polynomial curves. All right, now obviously, I can't calculate a slope in the way that we have done it in the past. I cannot do rise over run, okay, because there is no rise. It would be different here and here and here. It would be different all along the curve. But let's say at this given point along the curve, if I can draw the tangent line, can I find the slope at that point? And right here, it would be what? It'd be positive, wouldn't it? Okay, but how about if I picked a point over here? If I pick a point over here and I draw a tangent line and then I find the slope of that tangent line, what's the slope going to be? It's going to be negative. All right, so any point along this curve, the slope changes. It is always changing.
Juniors, S through Z, school pictures in the main gym. Juniors, S through Z.
So as I move along this curve, the slope changes at any given point along the curve. It's dynamic, all right? And to be able to calculate the slope at any point along that curve, all right, then I'm going to need to be able to apply some calculus, all right? And then going all the way back to, like, say, middle school, we can find the area of known shapes, right? That's a rectangle, length times width. If I had a circle, pi r squared, all right, I could find the area of any known shape. And then what did you do, like, as early as elementary school? If it was an irregular shape, what they have you do? They put it on graph paper, right? And then you counted the little squares, and then 2 half squares you put together and you estimated. So you estimated irregular shapes. All right, well, now we don't want to just do some random shape on a piece of paper. We want to apply it a little bit more. So if I've got a curve, and let's say in between, I don't know, this x value and this x value, I want to know the area of that shape. All right, this is a curve, so that's not a trapezoid. All right, it's going to be an irregular shape. I can't find the area of that without the use of calculus. All right, but we will, as we go through this, you're going to be able to calculate the area under a given curve, any section along that curve. All right, so to be able to do that, we're going to transition into this step by step. Okay, we're going to transition into this. So you've got pre-calc, which is where we were last year. Okay. Now, what we're going to do today, we're going to very specifically look at something called a limit process. Okay, and we looked at limits in general yesterday, or not yesterday, last year. Okay, so we're going to take this idea of a limit, call it a limit process, and that's going to transition us into how we're going to do our calculus. Okay, So like I said, today's a lot of conceptual understanding of this. Okay. Now let's take a look at a couple pictures here. And like I said, all of these are on my website. So if you want to download them later so that you have them in your notes and print them, you're more than welcome to do that. Okay, so this is, here, let's do the top of this. All right, we're going to look at the idea of a limit. And on this particular problem, it's going to be a tangent line problem. Okay, and we're going to do this tangent line problem. We're going to conceptually understand it using a limit process. Okay, so picture on the left, right here. All right, I've got some random curve, f of x. Okay, let's say at that point P right there, I can draw a tangent line. If I'm just using a straight edge, I can draw the tangent line there, right? All right, now, with pre-calc and just that information, can I find the slope of that line? Because I need 2 points on the line, don't I? And the only point on the line that I know would be right here. So I don't know another point on this line. So using only calculus, I cannot find the slope of that. Using only pre-calculus knowledge, I cannot find the slope of that tangent line. All right, now, let's take a look at this over here. All right, if I pick a random point Q and I draw a line through it, what kind of line is that? It's a secant line. This is on the paper. Okay, it's a secant line because it goes through 2 points on that curve, right? Now, with this being a secant line, and I know this point because I know the x and the y, because I know the function, the value of the function. I know x and y here. Can I calculate the slope of the secant line? I can. Now, if I choose to pick a different point Q on this line, again, I still know, I'm still going through this point P here. I know 2 points on that line. I could calculate the slope of that secant line. All right, if I pick another point Q on here, again, I could calculate the thing. Now, eventually, look what's happening. These secant lines, as I pick points Q closer and closer to P on the curve, what's going to happen to those secant lines? Eventually, it's going to line up with that tangent line, isn't it? Eventually, it's going to line up with that tangent line. So then I could approximate the slope of that tangent line. So right now, we're going to approximate the slope of that tangent line. Okay, because when I actually get to it, will I know a second point? I won't know a second point. But I could probably get a feel for this because what, this is a positive one, but that slope is getting, they're still going to remain positive, but it's going to get closer and closer and closer and closer to that slope of that tangent line. Okay, now let's stop and think about what's actually happening. Okay, what's actually happening? As I approach and I do this limit process, I'm picking Q's. All right, so if I want to be really, really accurate, I would pick lots of point Q's in there. So how many Q's am I ultimately picking, or how many Q's can I? I could let the number of Q's approach infinity. I could let the number of Q's that I pick approach infinity. Then I would, because the more lines I do, the more accurate my approximation is going to be for that tangent line. Okay, now, as I pick infinitely many Q's, what's happening to delta x? What's happening to the distance between P and Q? So when I pick this first one, my distance along the x-axis is from here to here. But as I pick this one, my distance between P and Q just got a little bit smaller, didn't it? And as I pick this one, that delta x, or that distance between P and Q, got a little bit smaller. So as I let the number of Q's approach infinity, delta x is approaching what number? Delta x is not approaching.
It's approaching delta x.
If I have the delta x is the distance from here to here. So when I pick my first Q, it's this distance. I pick the second Q, it's a shorter distance. As I pick another Q, it's a smaller distance. It's approaching 0. If I keep picking enough Q's on here and I get those Q's closer and closer and closer to my point P.
Seniors, L through R.
delta X is approaching
School
0.
pictures in the main gym. Seniors, L through R.
Okay, so as I pick infinitely many q's, as q's approach infinity, all right, and I'm picking q's closer and closer to my point P on there, my delta X is approaching 0. All right, this is a limit idea. This, as it gets infinitely close to it, but not exactly there, I can come up with some approximations. Okay, so this is kind of like a limit idea. Now, obviously, this whole limit process and the tangent line problem, all right, we will examine this multiple times, and as we move on into chapter 1 and chapter 2, you're going to see it more and more and more. All right, so this is considered a tangent line problem because what I am using the limit process there is with my tangent line. All right, now let's do this. Okay, let's do this with area. All right, I'm still going to use this idea of a limit, but I'm going to do it with an area problem. All right, so I'm going to be using a limit process. Okay, let's take right here a polynomial curve. And let's say I wanted to calculate the area between A and B under the curve. All right, well, it's a irregular shape, so we don't have a formula for it. But if I were to break it into rectangles, and notice what's happening to every one of those rectangles. On this first rectangle, I'm letting the top left-hand corner touch the curve. On this next rectangle, I'm letting the top left-hand corner touch the curve. On this rectangle, I'm letting the top left-hand corner touch the curve. Okay, in which case, can I not find the area of each one of those? Length times width, because I know this distance from here to here if it's a point on the curve, and I know this distance that would be along the x-axis. So I could calculate the area of this, plus this, plus this, plus this, and it would give me an approximation. Now, is that approximation going to be less than the actual value or more?
Less.
It's less because there's some empty spaces under there that's not accounted for. Okay. Now, this is with 4 rectangles, or n equals 4. All right, now let's look at this picture. Let's suppose I take that exact same curve and I up the number of rectangles. Okay, I went from 4 rectangles to 8 rectangles. So I'm increasing the number of rectangles. All right, and then again, that top left endpoint is landing on the curve, so I can calculate the area of each one of those and add them up. Is this going to be a better approximation or a worse approximation? It's going to be a better approximation because I have less white space there underneath that curve. Okay, now if I up the number of rectangles to 16, I get what? A yet even better approximation of that area under the curve. Okay, so what's happening? What am I doing with my number of rectangles? I'm letting the number of rectangles approach infinity. If I let the number of rectangles approach infinity, I'm going to get a better and better and better approximation. Now, as the number of rectangles approach infinity, what's happening to delta x? Delta x is this wide here, and then over here, delta x is a little bit smaller. Over here, delta x is even a little bit smaller. So delta x is approaching 0. As I let the number of rectangles approach infinity, delta x is approaching 0. That's your limit process. This is this idea of a limit. And what's it ultimately going to do? It's going to ultimately allow us to calculate the area under that curve, irregular shape. Okay, so like I said, today, very conceptual in nature, okay, very conceptual. You're kind of building the idea around this. Now, this is not the only time we're going to do this. I'm going to talk about this over and over and over and over until we get a grasp on this, okay? Let's do a little bit of vocabulary here before we move on. I think as I go through some example problems today in the homework, this is going to help. All right, so obviously, let's say I've got a f of x equals x squared. There's this nice little polynomial, quadratic. If I draw rectangles, look how that left, again, that I'm putting the left point of each one of those rectangles right on my curve. All right, so they're considered to be left-sided endpoints because the top left-hand corner is on the curve. All right, these are considered to be inscribed rectangles. okay, because they fall under the curve. All right, now, who says I have to use the left side endpoints? I don't, right? Because I can draw those rectangles any way I want. If I take that exact same curve and I draw a rectangle, but this time the rectangle's the top right-hand corner is landing on the curve. Top right-hand corner is landing on the curve. These would be called right-sided endpoints. Okay, and what's happening? What happens to those rectangles? They're going above the curve, right? So on this particular picture, if I try to estimate the area under the curve from 0 to 1 and I'm using right-handed endpoints, is that estimate going to be an overestimate or underestimate? It's going to be an overestimate because I've got all this extra space on top that I don't need. All right, these are called circumscribed rectangles. Okay, in the past, I have put these two vocabulary words on the first quiz. All right, you need to know the difference between inscribed rectangles and circumscribed rectangles. So just, heads up there, put a little star, write that down or something. I have put that on the first quiz. Okay, so that's really a preview of this limit idea. Okay, so now y'all look like you're bored because you're all falling asleep. I don't know what you're doing at home. All right, here at the beginning of calculus, we're going to have a lot of these type of discussions where you've got to mentally be engaged with me. You've got to think this process through because I don't want you to just memorize how to do integrals or derivatives. I want you to conceptually understand what we're doing because that's the only way come next March and April when we're doing AP calculus questions and we're trying to review for that test. The only way you are going to actually be able to do those problems is if you conceptually understand what I'm talking about. Okay? So yes, cranking out the problems is important. That's always been important in math, but conceptually understanding is going to be a major key point, okay? I know you just missed all that. I did cool little things with rectangles. I am recording this. I will try to as soon as possible. I'll try to get it online so you can see it. Okay, all right, so enough talking now. Let's go back and let's actually put some of this into practice. All right, does anybody, what time do we get out of here? I cannot. Okay, all right, so I got about 40 minutes. Okay, so we should be good. I think my laptop here is dying, so for the people at home, we don't want to lose the Zoom meeting. I'm going to plug that in before we get started. Okay, so we're going to look at a secant line example. All right, let's suppose we are given f of x is equal to 8 minus x squared, and we're given the point 1, 7. Okay, so I'm going to break this up in your homework just like you're going to do a part A, you're going to do a part B, you're going to do a part C. Okay. Basically, what part A is going to ask you to do, they're going to ask you to graph f of x. All right, and you are going to need a piece of graph paper. And if you're in the room, I would use the big graph paper, like a full sheet of graph paper, okay, as opposed to the little tiny ones, because tiny ones are not going to be good. On here, we're just going to sketch. All right, I'm just going to do a rough sketch. You're going to graph f of x and the secant lines that go through the point 1, 7. Supposed to be a 1, 7 there. And a point Q for x values of 3, 2.5, and 2. Okay, so part A is going to ask you to graph that and then graph all the secant lines. So we're going to do a rough graph here. It's not going to be a necessarily precise graph. All right, on your homework, I am going to expect you to use graph paper and be a little bit more precise. Okay, so first of all, if I just graph my 8 minus x squared, well, we know it's a parabola, we know it's upside down, we know the y-intercept is 8, correct? So I'm going to try to do a rough estimate here of 1, 2, 4, 5, 6, 7, 8. So I know the vertex of my parabola is right there. Now, technically, we could do a really accurate, because we can do our shortcut, right? We could do our 1, 3, 5. We could get that on there. If you do that, you're going to have a lot of extra points on there that I don't think that you need. Okay, this point 1, 0, or 1, 0, this point right here, 1, 7, is going to fall on the curve. You can plug 1 in and see that it is. So if I did a 1, 7, all right, but that's the over 1, up 1 point right there. Okay, so this is my 1, 7. Now I'm going to, I think if I've got enough colors, I'm going to try to color coordinate this. And it may be helpful to color coordinate this for you as well. All right, now each one of these points right here. All right, I didn't need to color coordinate that. If I want, can't I create an XY table real quick and just crank out some values here? So we can put the 2 on there, we can put the 2.5, and we put the 3. I need to know what those points are, right? So if I plug 2 in, let's see, 2 squared is 4, 8 minus 4, that's going to give me a 4. Don't let me make any mistakes here. If I plug 2.5 in, and I square it, and then I take 8, how about 1.75? And then if I plug 3 in, 3 squared is 9, this will give me -1. All right, so what I did with these x values right here, created a little xy table, plugged them into that original function just so I could graph some points here. Okay, so let's do the 2, 4 point in purple. And again, it's going to be a rough estimate since I'm not really on my graph paper. Let's put the 2.5 and 1.75. 2.5, 1.75. We'll estimate that to be about right there. 2.5, 1.75. We'll do that one in red. Hope my colors are showing up for you at home. There's 3, -1. So we'll hash mark for -1 right there. Okay, so there's 3, -1. All right, so like I said, we could have just graphed it, but I know I definitely want those points on there. Okay, so obviously it's parabola upside down. We're just doing a rough sketch here. So it says graph f of x, so I have done that. All right, and the secant lines through the 0.17 and each of these other points. Okay, now this is where when you're not on graph paper, it's not necessarily going to be the most accurate thing we've ever done. All right, but I want a secant line now through my purple point and that 0.17. All right, I'm going to do it this way so it's kind of really long. All right, as bad as my rough sketch is, there is a secant line that goes through the 0.17 and 2,4. Okay, now I'm going to use the red line, and this time I want it to still go through 1,7 and my red point, 2.5, 1.75. So the secant line that goes through those and then my last secant line, I want to go through the 1,7 and the 3,1. And like I said, if this was on graph paper, this would look so much better. That's why on your homework, you're going to do that. Ooh, let's see if I can. So hopefully you can see what those secant lines are doing. The purple line, and then the red line, and then the green line. Okay, good so far? All right, now I kind of wish I had not done this. So I'm going to try to erase this just so I've got some more room to write. I'm going to use tons of white out just to get rid of this so I got more room to write. Probably not the best way to get rid of that, but right now it's the fastest way. Okay. All right, now part B is going to ask you to find the slopes of those secant lines. All right, so I want to find the slopes of those secant lines. All right, so you can probably do those. That's just going to be some math calculations, right? Okay, so if I am doing, say, the purple line, that's why I color coordinated it here so we could maybe kind of organize a little bit. What's that going to be? It's going to be 4 minus 7 over 2 minus 1, which will give me -3. Don't let me make a silly mistake here. All right, let's see if we can do the red line. Okay, my red line. So let's do 1.75 minus 7 and 2.5 minus 1. I'm doing it with that 1.7 point every time. That gives me like a -3.5. Now let's do the green line. So that's going to be a -1 minus the 7, and then it'll be the 3 minus the 1. So what's that? -8 over 2, -4. Okay, so part B is going to ask you to find the slopes of that secant line. Okay, so far so good, right? Because that's just basic pre-calc stuff, nothing too challenging here. Okay, I'm going to go up to right about here. All right, now part C is then going to ask you to use the results to estimate the slope of the tangent line at 1.7. All right, so they're going to ask you to use those results you just got to estimate the slope of the tangent line. Okay. Then they're going to ask you to describe how to improve the approximation. All right, so first of all, do you know where the tangent line is at 1.7? Like if I were to draw, I mean, and granted, this isn't going to be massively accurate, but if I want the tangent line, because I'm not on graph paper, but if I want the tangent line, I'm going to, what color should I put it in? Let's try to use a yellow highlighter. If I wanted the tangent line, maybe, yeah, that'll stand out really good there. Okay, there's my tangent line, right? So take a look at those slopes. The green line was at -4, and then the red line was at -3.5. The purple line is at -3. So that yellow line, just estimate it, -2. All right. Is there, I mean, I'm asking you to estimate, so, you know, you could have said -1.5, you could have said, you know, whatever, you could have said -2.5. All right. But
As long as you didn't say like -7.
correct. Okay. As long as you didn't say something like -5 or -6.
Seniors, S through Z. Time for your picture, seniors, S through Z.
Yeah, so as long as, wow, that just is wiping out my entire class here. Okay, since we're recording this, I'm going to go ahead and finish this problem. Okay. All right, so hi, Caitlin. Okay, so we approximated it at about -2.5. Okay, so the second part of the thing says describe how to improve the approximation. All right, so this is what we were doing earlier with that tangent line. I picked a green point here, then I picked the red point, and then I picked the purple point. If I would have picked another point up here, it would have been even closer to the actual line, right? So I need to pick points closer to my 1.7. When I pick points closer to my 1.7, my delta x is going to 0. It's getting closer and closer and closer because that distance of delta x is going to 0. Okay, so you're going to do one just like this in your homework, okay? And to help this, all right, I would seriously use like rather large graph paper. All right, and depending on what the curve is that you have to do, all right, it might be, you just might need first quadrant. Okay, so I've got some larger graph paper over there. If you're at home, all right, you can probably look around on my website and download some graph paper. And if not, you could just go to any website and download some graph paper, because it's probably going to be helpful for this. Okay. Now it's about 10 after, so I'm going to keep going because we got to do a rectangle. We got to do an area problem. All right, so this is a secant line example. All right, now the rectangle one is the explanation, the limit process you missed because you went and got your picture taken. Okay, so I think mathematically, though, you're going to be able to do this just conceptually understanding what I'm going to do here. Okay, so we're going to take a look at an area problem. So it's my area of problem example. All right, so it's going to ask us to find the area of the region bounded by all of these curves. Y equals 4 over x, and then y equals 0, x equals 1, x equals 4. All right, and for right now, I'm going to tell you that we are going to let delta x equals 1. All right, eventually you're going to calculate your delta x or your distance between your x values, but right now I'm just going to tell you delta x is 1. All right, so you're going to find the area of the region that is bounded by these curves. All right, so it is going to help if we have a sketch. And again, this one probably does not have to be as precise, but we definitely want to sketch this. Now, I put this, I drew it, my coordinate plane there, in just the first quadrant, because looking at this, if I'm going to have, these are going to be vertical lines between 1 and 4, so it's going to be a vertical line here and here. Y equals 0 is a horizontal line here, and we know that this is going to be our rational function. So I only need first quadrant. So I can look at these a little bit ahead of time and decide if I need, both the first and the second quadrant, or if I need the whole graph or just the first quadrant. Okay, so let's, though, be a little bit more precise, and let's draw this kind of big. So I'm going to kind of make this kind of big in my sketch. I think it's going to make a little bit more sense if I do that. Let's make this about the same distance. So 1, 2, 3, 4. I'm just giving myself plenty of room here. Okay, so we know that sketch from last year, because we have memorized, is that. Okay, and so the only portion that I need to look at is that in the first quadrant. So I know my function is going to look like this. All right, let's go ahead and put our boundaries on, though, before we start. I'm going to have a boundary at y equals 0, which I'm going to have y equals 0. I'm going to have a horizontal line here that's going to be a boundary. Okay, I'm going to have a boundary at x equals 1. So I'm going to go ahead and put a little boundary in there. And x equals 4. 1, 2, 3, 4. I'm going to have a boundary there. Okay, now, so that we can be a little more precise, I mean, I don't want, like what we did in pre-calc, we just kind of did swishies in here, right? I don't want a swishy on this one if I'm trying to find the area or approximate the area. I want to be a little bit more precise. Okay, so where can I put this? Let's see, I'll do it right here. I could real quickly make a nice little XY table, and I could plot some points. I could plot 1, 2, 3, and 4 on here. All right, just so I could know exactly where this curve comes down in here. All right, so if I plug 1 into the function, 4 over 1 is just going to give me a 4. If I plug 2 into the function, 4 divided by 2 is going to give me a 2. If I plug 3 into the function, it's going to give me 4/3. Let's just leave it as 4/3. All right, if I plug 4 in, 4 divided by 4 is going to give me a 1 right there. Okay, so now I can be pretty precise, and I can plot those points. So 1, 4 is going to be right there. 2, 2 is going to be right here. 3, 4/3. So it'd be 1 1/3. So again, I'm going to have to estimate this one. right about in there. And then 4, 1 is going to be right there. Okay, so again, without graph paper, right there is my curve. Okay, that was a real sad drawing right there. Okay, now I'm not going to clutter this up too much with shading, but I'm finding the area of the region that is bound by these curves. Okay, so I want the area right here that's bounded by y equals 0, x equals 1, x equals 4. So right in here is what I'm trying to estimate the area of here. Okay, so I am going to give you some more pieces of information here. I am going to tell you to use 3 subintervals and left side endpoints. Okay, I'm using 3 subintervals and left-sided endpoints. Okay, so we're going to do what we had done with rectangles. I did say up here I gave you delta x equals 1. All right, if I use a delta x of 1, I'm going to have 3 rectangles. My subintervals are going to be my rectangles. Okay, if I'm going to do left-sided endpoints, okay, let's put this in green. Okay, so this first rectangle would come up. The left side is going to touch the curve. I would come over and then I would come down to there. So that's a left-sided rectangle. All right, and that's my first subinterval. All right, let's do my second subinterval would be at x equals 2. I would come up to the curve. All right, that's a left-sided endpoint. I would go ahead and draw my rectangle. And it would have a delta x of 1. Let's see, if I do my last one, I would start there at x equals 3. I would come up. I would let that left-handed endpoint touch the curve. I would come over and I would draw there. So I've got 3 rectangles there, correct? So there's the first one. I don't know that you need to shade it in like that. I'm just kind of playing with my picture right now. But I could estimate now because I can calculate each one of those rectangles, right? Length times width, length times width, length times width. I can add them up and I would be approximating the area under the curve that's bounded by that region. Now, is it going to be an overestimate or an underestimate? It's going to be an overestimate because I've got all this extra out here, right? So for right now, we're not going to get totally bent out of shape here with our notation. All right, obviously I'm trying to approximate my area. We're not using any official notation or anything like this. All right, so my first rectangle is what? It's going to have a delta x of 1. So 1 times, how tall is that? 4, someone said. All right, and then that's my first rectangle. And then my second rectangle still has a width of 1 times a height of 2. And then the last rectangle still has a delta x of 1 because I told you delta x is 1. And then it has a height of, what's that one? That's my estimate, right? So that's 4/3. And multiplying times 1 wasn't too bad there. So what's this going to be? 4 plus 2 plus 4/3. Okay, which is going to give me what? About 7 1/3. Okay, now technically it is area. I know if you wanted to label it units squared, you could. Later on in calculus, we're not going to be labeling this stuff. We're just, it's area. Okay, so you can do unit squared. You don't have to do it unit squared if you don't want to. You're approximating the area. We said this was going to be an overestimate of the actual area. All right. From earlier, what type of rectangles are these? Ah, that vocab word. The circumscribed ones because they go over. It gives us an overestimate. All right, so these are circumscribed rectangles because they are above. All right, and again, like I said on the online notes, that stuff that I had typed out at the beginning, you can print those out if you want that in your notes.
This is last call. Any freshman, sophomore, junior, or senior that did not get your picture taken this morning, head to the gym at this time.
Okay, now I could set this up and I could change it a little bit. I could tell you 3 subintervals, but right-sided endpoints. Okay, I maybe could, if I change delta x, could I have a more or less subintervals? Depending on what I let delta x be, I let delta x be 1. So this set up really nicely for 3 subintervals. But if I change the width of the rectangles, I could have more than 3 subintervals. I could have less than 3 subintervals. Okay, so it just depends on the kind of things that I actually give you. All right, so let's go ahead, because what time is it? It's 10:15. I still got about 20 minutes. Let's go ahead and do a right-sided endpoint. Let's keep the same boundaries. Let's still do 3 subintervals, delta x, but do right-sided endpoints. Okay, and then I know like Josiah, I see you're still writing.
I just wrapped up.
Okay, did you just wrap up? All right. I am going to try to upload this video later tonight, so hopefully it'll get there. Okay, so we're keeping everything the same, except what I want to do now is I want to do, I still want 3 subintervals, so use 3 subintervals. And right side endpoints this time, right-sided endpoints, right-sided endpoints. All right, I'm still keeping all the same curves, so I'll go write them down again just so we can see them. Y equals 4 over x was one of them. Y equals 0, x equals 1, x equals 4. Okay, now, so we need a sketch. All right, rough sketch, but again, I'm going to make it kind of big just so things kind of stand out a little bit. I'm going to make the distance here wide so that I've got plenty of room. I can see my rectangles. All right, now we've already created that XY table and plotted the points because we want to know how accurate we are here. So let's do the 1, 2, 3, 4. That was from our previous picture. We had calculated that at 4, 2, 4/3, and 1. Okay, just so you see where I'm getting those points at. All right, so 1, 4, 2, 2, 3, 4 1/3, and 4, 1. Okay, so then that was the curve. All right, notice on this one, I put the curve on first, and then I'm putting the boundaries on last. It really doesn't make any difference. Okay, I do clearly want to indicate where my boundaries are. I've got a boundary at y equals 0. Okay, so there's my y equals 0 line. I've got a boundary at x equals 1. So that's a vertical line. It puts me a boundary right there. I've got a vertical x equals 1. So basically, same picture we had just a minute ago. Again, this area in here is the area that I'm trying to estimate. Okay, now your picture is going to look different, right? Because I'm using 3 subintervals, but right-sided endpoints. All right, delta x is still 1, okay, because I gave you that. But to get 3 subintervals, I got to have a delta x of 1. So here's going to be my first rectangle, right? Now, when you draw it, if I'm using a right-sided endpoint, when I go up on the, I want to go up on the right-hand side, and I want to touch my curve. All right, so this would be delta x of 1. I come up, I hit the curve, but this first rectangle goes this way. Okay, that's a right-sided endpoint. And again, I could fill that in right there like that. All right, if I want to do a right-sided endpoint on my next interval, okay, I'm going to go to the right side of that rectangle. I'm going to go up. It's going to touch the curve because it's a right-sided endpoint. Then I'm going to come over here to the left. Okay, there's that rectangle. My last rectangle. Again, on that last interval, I'm going to go to the right side. I'm going to go up to the curve and then come over and form that rectangle. So on this particular curve, my estimate is going to be overestimate or underestimate? Underestimate. Are these rectangles circumscribed or inscribed rectangles? They're inscribed rectangles, okay? And then again, I'm not going to get, when you estimate the area here, okay, I'm not going to get overly picky about the math, okay, because right now I just conceptually want you to understand what's going on. That first rectangle has a width of 1 and a height of 2. Okay, the next one has a width of 1 and a height of 4/3. And the last one has delta 1, height of 1. Okay, so this estimate's what? A 2 plus a 4/3 plus 1. So what, 4 1/3? Okay, so a rough estimate of 4 1/3. So then that means, because now we've done the left-sided endpoints and the right-sided endpoints, this is the underestimate at 4 1/3. The overestimate was 7 1/3. So the actual area bounded by this region, if I shaded in that entire area, has got to lie somewhere in between 4 1/3 and 7 1/3. Okay, so right now we're just trying to approximate this stuff. All right, we're using the limit process. We can do it with two things. We can do it with those tangent line problems. We can do it with the rectangle problems. Okay, when we take a quiz here at the beginning, you're going to have to be able to draw accurately. I'll put graph paper on the tests and quizzes, and you'll have to be able to clearly show right-handed endpoints, left-handed endpoints, do some shading. You always want to add those boundaries to the picture because we need to know the area that's being bounded that we're trying to find the area from. Okay, that was a lot of information today. All right, we started with a lot of conceptual ideas. All right, it's not going to be the only time we're going to talk about that. We will do it more than just once till you get the idea of this. All right, you're going to practice some of the problems kind of like what we have done in class here. All right, 10:35. Yep.